Okay, thank you, Shuhan. So I'm going to discuss this paper that I wrote back in October with Raghu Mahajan. I should say that early on, both Nadi Seiberg and Shuhan were also collaborating on the project, and although they had to decouple when the pandemic hit, I owe a lot to discussions with them on this topic, and in particular, it was really Nadi who suggested the problem and convinced me that it wasn't completely understood. So the basic aim of this paper was to really nail down the exact quantum field theory relationship between the minimal model conformal field theories and the Lagrangian theory of the Coulomb gas scalar. So in other words, can we understand the Coulomb gas formalism as a statement about local quantum field theory rather than some sort of seemingly ad hoc set of rules for computing minimal model observables? So that's kind of a problem straight out of the 1980s, but we're interested in it now because it seems to be the quickest route to clarifying and potentially really deriving this relationship between the large P limit of the minimal string and the JT model. And for me, at least, that's an interesting question because it fits into a larger program where we try to understand the sort of universal quantum mechanical aspects of black hole physics through connections with random matrix theory and 2D quantum gravity. So I'm going to spend a little bit amount of time on this motivation since I think most of you are already familiar with it, and then the rest of the talk will just be two-dimensional conformal field theory. So, evidence has been gathering for 50 years now that black holes behave in many ways like isolated quantum mechanical systems. So they have a finite entropy, they radiate, they scramble information quickly. We have worked examples in string theory. But to my knowledge, every black hole that we managed to understand microscopically turned out to be a very complicated, strongly coupled quantum mechanical system. And there are really pretty general arguments why that should be the case. Now, in some cases, you can study those black holes very precisely, sort of an exquisite amount of precision that usually relies on requiring a lot of symmetry and some pretty heavy duty machinery. And you might suspect that those very powerful techniques are not really tied in a fundamental way to the universal features of interest. So, if the highly symmetric black hole is our hydrogen atom, then you have to keep in mind that while the hydrogen atom is solvable, nuclear physics is basically impossible. So, when a quantum mechanical system becomes sufficiently complicated, the type of question that you try to ask and answer, as well as the technique, has to change. And that's sort of the entry of random matrix techniques in the physics literature. So if the generic black hole would just be described by some hopelessly complicated, strongly coupled quantum system, then rather than try to solve it exactly, we can be optimistic and hope that certain aspects will be at least well approximated by random matrix theory, and then try to compare universal features. So that has a chance to work because random matrix theory really groups quantum mechanical systems into the coarsest possible universality classes. So because of that, it's able to capture the most universal behavior. And similarly, there's a tremendous amount of universal behavior in black hole physics. So, the area law holds in any dimension. The near extremal limit always yields ADS2-like factors in the near horizon region. They all scramble quickly, the list goes on. Because really most calculations that are done either rely on the presence of the ADS2 throat or exponential redshift. And for me, at least, scaling onto the spectral edge where all of the universality and random matrix theory resides looks a lot like zooming in to the extremal limit, which is also universal. So that's just to say that you expect some features, and in particular, potentially some universal features of black hole physics to be reproducible using random matrix theory. Now, one of those particularly universal features is the existence of this extremal limit and the ADS2 factors that it produces. So black holes with an extremal limit, they tend to have well-behaved thermodynamic properties at low temperatures. And experience has taught us that we can hope to describe them using actual isolated and in particular non-gravitational quantum mechanical systems. And they all have this particular feature that as you dial the hole towards extremality, an approximately ADS2 throat opens up in the near horizon region. And what that extremal limit really buys for you is a clean separation between the black hole and its asymptotically flat environment, in the sense that the response of the hole to certain classes of external perturbations is approximated and really controlled by the dynamics in this throat region. So in that sense, there is something two-dimensional about the black hole. Now, that might not be the case far from extremality. I don't think we really know. Schwarzschild certainly doesn't have a throat, and it also has pretty non-standard thermodynamic properties that you might imagine are difficult to reproduce with a non-gravitational system. But putting that aside, even in the near extremal case, there are complications, essentially because of the low dimensionality of the effective ADS2 throat. So that's a well-known and old problem. It's just because low dimensional systems with long range forces, they suffer from violent infrared divergences. And this JT model, which is studied a lot lately, is really just the exact theory of that infrared divergence. That's its main purpose in life. But even though it's really designed to do this one specific thing, it turns out to be surprisingly effective, and it captures lots of the interesting features of near extremal black holes. And in particular, it really nails some of these expectations that we have coming from random matrix theory. It does it too well in the sense that this model really is just a random matrix integral. So, you have this strange situation where you have an extremely crude approximation to the dynamics in the extremal throat, but it gets a lot of things right on the nose. And you'd like to kind of understand why that is without over-interpreting the model. So the result, which is important for us, is due to Saad, Schenker, and Stanford. They showed that the genus expansion of the gravitational path integral for this model is just the genus expansion of a double-scaled matrix integral. And in that description, there's a particularly important role played by the leading order density of states. So you can read that off from the disk approximation to the gravitational path integral. And for the JT model, it just has this sinh root E behavior. I suppress everything but the dependence on the energy. And the point is that Seiberg and Stanford noticed that if you take the density of states for the minimal string, which is another class of two-dimensional gravity theories, which are known to have matrix descriptions, and you take a particular scaling limit, so you send P off to infinity and you rescale the energy in a certain way, actually you will land right on the JT answer, okay? So that's an interesting observation, and that limit was then tested on other genus zero observables in the minimal string by Mertens and Turiachi, and it seems to be true, at least at genus zero. So, that raises the question, well, what does string theory in less than one dimension have to do with four-dimensional black hole physics? Now, the JT model is not the only 2D theory of gravity with a random matrix description. As I said, you have an entire class of theories, which, normally you would view as worldsheet theories for a minimal string. They involve taking a minimal model, coupling it to dynamical gravity through the Louisville field. And those models are known to have matrix descriptions as well. So the old heuristic for this correspondence was that you view the matrices as some particular regularization of the path integral, like putting quantum gravity on the lattice. So you try to replace the integral over metrics and the sum over topology with a sum over random triangulations, and then take a continuum limit to produce the continuum theory. And the statement from the early 90s was that these discrete models really are in the same universality class as the minimal model coupled to Louisville. And there's a particular class of these minimal theories, which involve the 2, P minimal models coupled to Louisville, which are described by single matrix models. And as I said, if you take certain quantities which are computed in these models and you send P to infinity, you find agreement with calculations which are done independently in JT gravity. So what you would like to understand is why this is the case. Now there's kind of a cartoon heuristic for it, which is that when you send P to infinity in this line of minimal models, the matter central charge actually goes off to negative infinity. And the Louisville central charge has to compensate, so it becomes large. And that's really just a semi-classical limit for the metric, the conformal factor in the metric. So the fluctuations freeze out and you're left basically with an integral over the classical solutions, which are the constant curvature surfaces. And that's basically the definition of JT gravity modulo the sort of extrinsic wiggles in the asymptotic region. So, there are other sequences of minimal models that you could take whose central charge also goes off to negative infinity, and the same reasoning would seem to apply. So those limit points might define other interesting calculable generalizations of the JT model, but it seems kind of hard to just guess what that limit point will be. And so what you would like to really do is to just do some formal manipulations within the path integral, as has been suggested for JT gravity, and kind of guess the answers quickly. So that's sort of why we'd like to understand this, how seriously we can take this Lagrangian description for the minimal model, because it will then allow for very formal but kind of easy derivations of this type of correspondence. And I just would say more generally, this random triangulation heuristic suggests that many models of 2D gravity could be approximated in some sense with random matrix theory. So there are obvious obstacles. There's the C=1 barrier. If you take the continuum limit, you might not end up in the right phase. It could be some gross branched polymer phase. Even if you manage to surmount those difficulties, then you have to understand, is there actually some relation to a black hole Hamiltonian? Because lots of these models, they don't involve a single matrix, they involve multiple matrices.
So could you go back to the previous transparency?
This one or the one before?
No, this one. So this last statement that the random triangulation suggests that it should be approximated by random matrix theory. What exactly do you have in mind? So,
well, I just have in mind the original heuristic for why this matrix enters the picture, which is just that you're trying to simulate the integral over metrics and the sum over topology with random triangulations, and you approximate it and try to take a continuum limit. That there are known difficulties doing that beyond C=1 matter.
Right. That was the old relation between the matrix integral and the random surfaces, right?
Yeah. Yeah. So what I'm saying is,
why? Yeah. So what I don't see is, okay. Okay, fine. Yeah, then you have this question about the black hole Hamiltonian, which is what confused. Okay, fine. Yeah.
Yeah. So we have an independent reason to believe that black holes should be related to 2D gravity through an extrema limit, and we believe that they should be approximated in some sense by random matrix theory. And it's either an extraordinary coincidence that we also have a heuristic that 2D gravity should be related to random matrix theory. Maybe it will be useful, maybe it won't, but the result on the JT model kind of completes the circle in the sense that that old relationship now really is relating sort of the extremal throat to this Hamiltonian. So, could be a wild goose chase. I don't think when you're starting out, but it looks suggestive to me. And that's kind of why I'm interested in the question. Any other questions? Okay, so what we would like to do is to understand how to really derive this relationship between the JT model and this limit of the minimal string. I'm not going to do that in this talk, but we're going to try to make progress in that direction. So Seiberg and Stanford suggested that the way to proceed would be to use this free field realization of the minimal model coupled to Louisville. And then there are some sort of formal field redefinitions and limits that you can take within the Lagrangian, which seem to sort of land you on this JT description of the limit. But what we're going to see is that there are several delicate global issues involved in that description, in particular compactness of the linear dilaton, a particular BRST quotient that you have to take. There's very subtle questions about truncation of perturbation theory and subtleties in the reflection of reflection identification. So there's lots of very tricky points in this Lagrangian description. And most of them are really only important for higher genus calculations, where to my knowledge, no real comparisons between JT and the minimal string have been made. So, hopefully taking these effects into account will either allow for a rigorous derivation of this large P duality or some refinement of the statement. Okay, so the model that we're going to end up discussing is, you could call it a BRST quotiented compact time-like Louisville theory. And that's obviously a mouthful. We're going to try and sort of unpack it step by step. But I want to give you sort of a roadmap for where we're going so that there aren't any big surprises along the way. So the first sort of key observation about these models is that although the background charge in the linear dilaton breaks the scalar field's continuous shift symmetry, there's just a term linear and phi sitting in the action. The exponential of the action can still be invariant under a discrete shift because for us, Q will be imaginary and the Euler term is quantized. So if we gauge that discrete symmetry, that will make the time-like linear dilaton compact, and it also introduces winding modes into the spectrum. And that's going to be important because one of those winding operators will be sort of the right-moving completion of this BRST current first introduced by Felder. And the statement is that the cohomology of that BRST charge actually isolates the minimal model operators, so sort of the irreducible representations of the Virasoro algebra within this much larger linear dilaton Fock space. So it sort of answers the question, you know, what is special about the minimal model operators within the full linear dilaton theory? And one sort of kinematic clue that you are going in the right direction is that the supertrace in this big BRST complex does reproduce the full minimal model torus partition function. And it does it through very delicate cancellations between states with both momentum and winding. Okay, so the sort of important ingredients in the kinematic construction are just compactness of the time-like linear dilaton, the role of these winding modes, and getting the full left plus right BRST complex nailed down. Now, when we go to study the dynamics, it will be important that at a particular radius, these models have two marginal operators corresponding roughly to the Dotsenko-Fatayev screening charges. So if we deform by them, we get something that looks, at least formally, like a BRST quotiented compact time-like Louisville theory. It actually will have many interesting but pretty non-standard properties. So for instance, you know, one way to try to understand the dynamics is to look at the zero-mode quantum mechanics. And there you will see immediately that the Hamiltonian is not Hermitian, but it actually does turn out to be PT symmetric and exactly solvable. And what you will see if you work out its eigenfunctions is that they have support actually on an infinite number of plane waves, which seems to support this idea that the correct interpretation of this model has an infinite reduction in the number of independent states. So in space like Louisville, when you study the zero-mode quantum mechanics, you just see scattering states coming in, bouncing off an unbounded potential and going back. So the one momentum gets related to its reflection. Here, a momentum will get related to infinitely many other plane waves. Okay, and then if we try to take these marginal deformations seriously and treat them with conformal perturbation theory, that will allow to reproduce the Coulomb gas calculations of the minimal model correlation functions. You have to understand how it is that two-dimensional surface integrals can be factorized into products of the Dotsenko-Fatayev-like line integrals, but that's actually rather well-known technology. An important distinction will be that in contrast to space like Louisville, these resonance correlators that we need to compute, they'll actually be finite because the zero mode is compact. So in this old Goulian and Lee approach to resonance correlators in space like Louisville, if you manage to find a correlation function which can be screened by an integer number of exponential interactions, then inside of the path integral, there's actually no damping for the zero mode. And so you integrate over a non-compact direction in field space without any damping and you get a divergence. And that's reflected in the fact that there are poles in the DOZZ formula at precisely those momenta. But here we'll be doing an integration over a compact cycle, so we don't get a divergence. You just pick up the factor of the radius. And we'll also have a nice sort of clean kinematic derivation of the fusion rules in these models, which however does rely on truncation of perturbation theory in these models, which is also sort of a non-standard feature. Okay. So this slide is just to set some notation for the rest of the talk. So if we choose two integers, p and p prime, that fixes a specific diagonal minimal model. The things which actually show up in calculations are usually the square roots of the ratios of those two integers, which I'll call alpha plus and alpha minus. The central charge for these models can all be, well, they are all less than 1 and they can be negative. And there's a finite list of Virasoro primaries labeled by two integers R and S, and the conformal weights are here. R and S are bounded by P and P prime, and sort of the defining feature of these models is that the OPE closes on a finite number of primary operators. Okay, so I'm not going to focus on the abstract characterization of these models. They can all be solved without ever referring to a free field. We're interested in the description in terms of a free field, which is the Coulomb gas formalism. So, you know, it was known pretty early on that lots of two-dimensional statistical models were normalized onto a scalar field at criticality. And the reason that that can happen is because a 2D scalar with background coupling to curvature can realize really any central charge. And it has lots of exponential operators which can realize almost any conformal dimension. So there's lots of room inside of this model to put what you are looking at. And it suggests that many fixed points could be described or embedded within such a model. And in fact, most rational conformal field theories do have descriptions in terms of multiple free fields. But for us, if we're just considering the minimal models, the standard free field realization only involves a single scalar field, which I'll call the time-like linear dilaton. Time-like just means that this Q parameter is strictly imaginary. So that model first entered the physics literature in a paper by Chodos and Thorne. They were trying essentially to change the critical dimension of the bosonic string, and that's still in some sense the way that the model is used today. But a decade later, Thorne returned to it because he wanted to understand better the Katz determinant formula. And he actually was able to work out explicit expressions for these singular vectors in the Fock spaces, and that's going to be an important paper for the work of Felder that followed. And there was sort of a parallel development by the mathematicians Feigen and Fuchs, who were also trying to prove this Katz determinant formula through this sort of auxiliary route through the linear dilaton Fock space. So, you know, the reason that all of these authors are adding in extra ingredients to study a problem which can be phrased purely in terms of Virasoro representation theory is because the Fock space for the free scalar, it has extra structure, so it's easier to study. So it has current algebra, not just the Virasoro algebra, so it's easier to handle, but you know, there's no free lunch. It's also related in a pretty non-trivial way to the Verma modules for the central charge less than 1 and the degenerate values of the weights. Okay, so what you're really interested in is calculating the zeros of the determinant of this matrix of inner products between descendants in a Verma module, but that's kind of a hard problem. So you introduce this extra Fock space and try to factorize that hard problem into two simpler problems, which is studying the maps into and out of this Fock space, okay? So what these guys really were doing was nailing down the structure of the Hilbert space of the linear dilaton, but they didn't care about dynamics because they're just doing representation theory. Now, those sort of more mathematical developments first really made contact with the minimal models through the work of Datsenko and Fateev, who invented sort of a, at the time at least, seemingly ad hoc prescription for computing minimal model observables using free field techniques. So they, you know, they said, Feigen and Fuchs showed us that a free scalar gets the representation theory in these models correct. Maybe it's also the case that you can use a free scalar to calculate the actual correlation functions in these models. So they took this time-like linear dilaton, you set Q to whatever you need it to be to reproduce the central charge, and then you just go through the list of exponential operators and pick out the ones whose dimensions match those of the minimal model primaries. Now, it's still a free theory, so genus zero correlation functions are just given by free field expectation values with a modified selection rule, which I'll discuss later, but those obviously don't reproduce the correct correlation functions in an interacting theory. So the solution, according to Dovzhenko and Fateev, was to use these two operators. They're exponential operators with momenta 2 alpha plus and alpha minus. They have dimension 1, which means that commutators of the Virasoro generators with these operators are total derivatives, so that closed contour integrals of these operators actually commute with the Virasoro algebra. So although these operators are not there in the minimal model, the idea is to try to use them to change the correlation functions of the linear dilaton into those of the minimal model. And as I said, the line integrals of these operators, they will commute with the Virasoro algebra, but since they carry U1 charge, they don't commute with the current, so you can use them to satisfy the selection rule. Okay, so you try to screen the background charge asymmetry and produce non-zero values for correlation functions that would otherwise vanish.
So that operator e to the 2I alpha plus minus phi, it's a holomorphic operator. So h bar is 0.
So almost all of this work was always done holomorphically. And what we'd like to do is understand the full quantum field theory. And it's illuminating actually, because as I'll describe, this is also the same operator which Felder is using for his BRST construction. And so it looks like there's sort of dual roles being played by these special weight 1 operators in the holomorphic Coulomb gas story. But if you go to the full quantum field theory, what you will see is that these operators that you use as screening charges, they pick up right moving pieces and they basically become marginal operators, which we will then try to deform by. Whereas Felder's BRST current picks up winding instead, so it has spin and it'll behave like a BRST current, okay? But right now, all of this is just being done holomorphically. You don't know, you're ignoring all global questions like, is the field compact? You know, is it a discrete spectrum? It's not being considered.
But they were computing the correlation function of the non-holomorphic minimal model? Or?
Let me discuss. I'm going to go through what they did. And if you still have questions, then let's definitely litigate it. Okay, so their prescription was you start with something which is not really physical. It's the holomorphic part of a correlation function. In order to reproduce that, you look through your list of exponential operators, find the ones whose dimensions match, put them into the correlation function in the linear dilaton theory, and then you just add in as many of these screening charges as you need in order to satisfy the selection rule, okay? Now, without any justification for this prescription, the contours in this formula are not fixed, okay? And in general, there will be multiple independent contours, each corresponding to a different conformal block. So the way that you determine the actual correct relative coefficients between all of these terms is to combine the left moving calculation of this correlator with the right moving piece. And then you require locality in the final answer. So no branch cuts, okay?
So I have a question here. So to specify a conformal block, you have to say what the representations are in the internal channels. So is there a simple way of saying if I represent the conformal block by a certain kind of trivalent graph and choose the internal representations, what the contours should be?
Yeah, you know.
I guess that means no. Okay.
Well, it doesn't mean no, it means I don't know the answer. You know, what these guys are really doing is cooking up integral representations for the blocks, right? Like they kind of knew that the 4.1.
But what you just said, and I agree, is that they're defining a vector space. But I'm asking for finer, right? The choice of different choices of contours give linearly independent functions. And they are the span over the different homology classes of contours spans the vector space of conformal blocks. So I was asking for something finer if I choose a basis for the space of conformal blocks, can I find a corresponding contour prescription?
I think the answer was eventually understood to be yes, but not in the original work.
I think you can get some insight into it by just watching computing the exponent in various channels. So depending on how you run the contour, you can draw the diagram with kind of like a tree diagram.
Yeah, exactly.
And then
right.
the exponent just add up because you're essentially doing free field calculations.
Right. Yeah, I
doesn't
agree.
tell you which state flows in which channel.
Yeah. So if you have a basis that looks like a cone, then you would take the integral of, well, actually, it would be something like that. You would successively take contour integrals around more and more of the successive products.
Yeah, I don't know the answer to your question. The point of this project really is to kind of eliminate this part of the discussion and just treat it with conformal perturbation theory. But yeah, maybe we could talk later. Okay, so that's the procedure which is commonly known as the Coulomb gas formalism. And at the time, it looked like a clever trick for finding integral representations of the blocks. But I think the physical interpretation is a little bit unclear. And it also only worked at genus 0. But it started to connect with what I would say are more central ideas in quantum field theory with this work of Felder. He basically identified this hidden kind of mysterious Brst structure in the construction. And once you know how to sort of project out all of the extraneous unwanted states in the linear dilaton, then you can start to compute things on higher genus surfaces. So he was able to compute some genus 1 observables. So let's say basically what he did. The most obvious question after the work of Vlasenko and Fateev is, what is the special status of these minimal model exponentials? So what singles them out from the much larger space of operators in the model? And Felder's answer was basically to reinterpret the construction of Feigen and Fuchs and also these explicit expressions for singular vectors that Thorne had worked out as a Brst quotient of this linear dilaton Hilbert space. So he constructed a series of Brst maps using this same operator, e to the 2i alpha minus phi, but importantly, it's not always a single integral, it can be multiple integrals. So it's a little bit funny, but those are exactly the things which had shown up in Thorne's representations for the singular vectors. Okay, and so he made these maps from Fock space to Fock space. You can show that the image is always in the kernel of the next map, so it's okay to pass to the cohomology. And what he found is that the cohomology of these charges in the minimal model Fock space actually just yields the irreducible representation of the Virasoro algebra. Something a little bit stronger than that, actually, I'll say in a moment. But it's important that this complex is infinite in both directions. So it's actually involving, in an important way, all of these other extraneous operators that are there in the linear dilaton, but they're not supposed to be there in the minimal model. And he actually showed something stronger, which was that actually the only cohomology in this entire complex sits within the minimal model exponentials Fock space. Okay, so everything else is either not Q closed or it's Q exact. Okay, so that's sort of what I view as the old holomorphic Coulomb gas formalism. And now we kind of like to package everything up into a local quantum field theory and try to make sense of it as best we can. Okay, so we're going to slowly try to build up to this Brst quotiented compact time-like Louisville theory piece by piece. Okay, so we can start at the very bottom, which is just a free scalar without a background charge. So Q is equal to 0. And for the moment, we will just work holomorphically. We're not going to pay attention to global issues like compactness. So the model has a U1 current. You can expand it into modes. Those modes are just the Fock space creation and annihilation operators. They obey the Heisenberg algebra. The energy momentum tensor is just the square of the U1 abelian current, which means that the Virasoro generators are quadratic in the current algebra. So in my conventions, an exponential operator, e to the I alpha phi, will have weight alpha squared by 4. Each of those operators defines a state on the cylinder by the state operator correspondence, and it's primary, so it will be annihilated by all of the positive modes of the Virasoro algebra and by all of the positive modes of the current algebra. And for each such state, we can just take all the current algebra descendants, and that is what I will mean by the Fock space associated to an exponential operator in the linear diatom. Now, there's one obviously important current algebra descendant, which is the one at level 1 that corresponds to the current, and it's easy to check algebraically that it's annihilated by all of the positive modes of the Virasoro algebra. So that means that the current algebra...
Are you saying that this current is conserved with Lagrangian, is not symmetric under translations under phi?
So right now we're discussing the model without a background charge, and then
sorry.
we turn it on and see
Sorry,
how.
sorry.
Okay, so the Fock space is an irreducible representation of the Heisenberg algebra, but it contains multiple representations of the Virasoro algebra. Obviously, there's nothing wrong with this level 1 descendant. It doesn't have 0 norm, but it is annihilated by all of the positive LMs. Now, when we turn on the background charge, that will add an improvement term to the energy momentum tensor. Has to be a total derivative, and it is. It's just d squared phi. And it's helpful to think about that like a twist of the energy momentum tensor by a derivative of this current. So that improvement term mixes the Virasoro and current algebra generators, and all of the generators in the Virasoro algebra will pick up a piece linear in the current algebra, since the energy momentum tensor has a term linear in the current algebra now. Okay, and in particular, that changes the central charge from 1 to 1 plus 6q squared. Now, since L0 picked up a shift, the dimensions of the exponential operators will also shift under this addition of the background charge. So they will pick up a term which is just proportional to their momentum. It's this IQ alpha by 2. And the background charge, importantly, also affects the commutation relation between the L's and the J's. So there's an extra term proportional to Q. And that affects the structure of these Fock spaces. So if you just look at sort of the simplest commutation relation, L1 with J minus 1, you pick up a new constant on the right-hand side. So previously, this level 1 current algebra descendant was annihilated by L1. Now it's not because of this constant term. So you act with L1 and you get the identity. Okay, so that's a little non-standard. Another way to say it is just that this current is no longer primary. It picked up this anomalous term in the OPE with the energy momentum tensor. Okay, and what Pagan and Fuchs did was really to work all of this structure out for all of the important Fock spaces of interest. The one other important effect of the background charge is this difference in the selection rule for the local correlation functions. So if you take this basic commutator again and you take its adjoint and you ask that the Virasoro algebra and the non-zero modes of the current algebra have their standard adjoints, then you will see actually that J0 dagger is J0 plus a constant piece. So now if we insert that into a string of exponential operators, if you act to the right, you will get the sum over the momenta, and if you act to the left, you will get this constant. Okay, so, in the theory, without the background charge, all of the momenta have to add up to 0. Now they need to add up to minus 2iq, and since q is imaginary for us, that's a real number. And it's also going to be important later when we look at the correlation functions that the resolution of the identity will be changed by the background charge. Okay, there's another way to derive this selection rule, which I like more, it uses the path integral. So we imagine splitting up the field phi into its zero mode and its non-zero mode piece. And then we're going to try to just do the integral over the zero mode separately. So if we have a string of exponential operators whose correlation function we'd like to compute, you can just track down where the zero mode shows up in the integrand. You'll get a piece from the background charge term because phi entered linearly. And you'll get a piece from all of the exponential operators, but it won't show up in the kinetic term. So it enters linearly, and you can treat it like a Lagrange multiplier. And that will also give you the selection rule, and it also shows you how it will work on higher genus surfaces. You basically replace the 2 in that formula by the Euler character. Okay, so that was all just sort of kinematics with the free theory. No obvious relation to the minimal models. The original work on two-dimensional conformal field theory introduced the minimal models. They demonstrated that there was only a finite number of primaries appearing in the OPE, but they didn't actually calculate the numerical values of these three-point functions. However, they did show that the null state decoupling conditions lead to ordinary differential equations for the minimal models four-point functions. And those ODEs, they're kind of generalizations of the hypergeometric equation. They have solutions with integral representations. And Datsenko and Fateev basically realized that those integrals could be represented in terms of integrated free field correlation functions. So that's sort of the big insight that allows this to work. Here are a couple of formulas that they needed. You're familiar with the expectation value of the exponential operators in the free theory if you are sitting on values of the momenta that satisfy the selection rule. They went through and just picked out values of the momenta, which were linear combinations of alpha plus and alpha minus, so that the dimensions of these operators would match the dimensions of the minimal model primaries. And they also needed these two h is equal to 1 operators, which are not inside the CATS table, but they're going to be extremely important for getting the dynamics correct. So these operators, they carry U1 charge, but they commute their integrals, if the contour is closed, commute with the Virasoro algebra. Okay, so you can use them to satisfy the selection rule without altering the conformal properties of the correlation function, just as numerical value.
I have a question here. I mean, if one's really careful, in general, you need to include co-cycle factors. Do they actually enter here? Or can you just safely ignore that?
Yeah, I haven't, well, there are some phases that you have to be careful with in the BRST construction because, well.
I mean, you need things to commute properly and really commute. And often, you know, for example, in the Frenkel-Katz-Siegel construction of affine Lie algebras, it just doesn't work unless you include the co-cycle factors.
Yeah. I mean, the way that this construction really works is that you sort of do a bunch of stuff in the middle that doesn't necessarily make sense, but then you impose a consistency condition at the end, so you're sort of guaranteed to get the right answer. So I think people are not necessarily very careful with the phases. There is going to be issues about mutual locality, especially in Felder's construction, but you can kind of be sloppy in this case and still get the right answer is I guess what I would say. Anyway, this is not the approach which we're trying to take. I'm just reviewing what's been done. Okay, so you're trying to reproduce this full correlation function in the minimal model. So you start with this holomorphic piece of the correlation function. You insert the vertex operators whose dimensions match, and then you put in as many screening charges as you need to satisfy the selection rule. There's no sort of principle which fixes the specific combination of contours. Each contour corresponds to some block, and the correct combination is determined by combining the holomorphic piece with the anti-holomorphic piece and requiring locality or the absence of branch cuts in the final answer. So sort of the textbook example of this type of calculation is one for which you choose the operators so that you only need to do a single screening charge insertion. All right. So you just insert one screening charge, you pull the integral out, evaluate the free field correlation function, that gives you an integral over one variable. So that integrand has potential branch points, and it has two independent contours in this case, which we'll take to be from 0 to z and from 1 to infinity. And the point, or at least the observation due to Dotsenko and Pateyev, is that the full minimal model coordinator, it has to be proportional to a sum of the products of the holomorphic and anti-holomorphic calculation that we're doing on this slide. So really the name of the game is nailing these coefficients xij, which appear as relative coefficients in the different terms. And the correct combination is determined by requiring locality, or the absence of monodromy, when you put the whole thing together. Okay, so in this case, if you take the point z around 0 and around 1, you will generically generate monodromy. It will mix the different functions. In this case, the monodromy around 0 is diagonal, so you know that X has to be a diagonal matrix. It won't be diagonal around 1, but there's some other basis of functions you can choose which does have that property. And so if you manage to get the linear change of basis right, then you can just solve for these coefficients X up to normalization. The normalization is actually more involved to compute, and really the easiest way to do it, I think, is using two-dimensional surface integrals, which I'll discuss later. But so, once you run that procedure, you get an expression for the 4-point function, and then you factorize it onto 3-point functions to determine the fusion rules. Okay, so what we would like to do is kind of rephrase that in terms of the command do conformal perturbation theory. And that will sort of take care of the dynamics in this BRST quotiented compact time-like variable theory.
Sorry, I don't think the Xij is going to be uniquely determined, because there are different modular invariant combinations of left and right.
Well, the diagonal models only have scalar Virasoro.
Who chose the diagonal models?
Well, I think, well, that's a good question.
That's the point. That's the point. If you just impose that the correlators make sense, there are going to be several solutions, because there are different modular invariant combinations of left and right. So when you do conformal perturbation theory, somehow you must be inputting a particular choice of.
Well, I'm already going to know the spectrum. It's all going to be spin zero primary operators, right? So.
Why wouldn't you describe it by saying that if conformal perturbation theory is consistent, it will generate one of these solutions of those conditions?
So, okay, which one? Probably the diagonal one.
Probably, yes.
Well, and then what about the others?
Yeah, I don't know how to describe the non-diagonal models in this Louisville description that I'm going to use later. I think it's an interesting question, but yeah, it's kind of separate from what I'm doing. Any other questions? Okay, so the last sort of piece that we're going to want to try to incorporate in the full quantum field theory is Felder's BRST construction. And this is kind of a pretty technical, delicate piece of machinery. I think in general, when there are zero norm states in the game, it makes sense to look for some type of BRST structure. They usually go hand in hand, and it's not as if Felder just pulled this thing out of a hat. So he already had expressions of Thorne for the singular vectors in these Fock spaces, which involve these multiple contour integrals acting on exponential operators. So he wanted to try to interpret those as BRST exact singular states. And then what he basically did was to combine those expressions with this analysis by Feigen and Fuchs, which told you where all of the different singular vectors were in each of the different Fock spaces to set up this BRST complex. So he makes a bunch of maps from Fock space to Fock space. The image is always in the kernel of the next, so he can pass to the cohomology. And you have to very carefully check where each vector in each of these Fock spaces go under these maps. If you just try to do it in the most general case, it's pretty intimidating, and I don't think I will manage to convey it to you in a talk. So I think it's better to just do a couple of simple examples, which hopefully convey the flavor and sort of show you how things are supposed to work. So one very simple example is the identity Fock space. So that's F11 in the middle. The Fock space sitting to its right is actually the one that involves this special operator e to the 2i alpha minus phi, okay, which is what I'm going to call the BRST current. Now, since there's not supposed to be any cohomology in that Fock space, it had better be the case that some state in the identity Fock space gets mapped into that exponential operator under the action of this BRST charge. And in this case, it's just a single integral of the BRST current, and it's not hard to see that it's just going to be the U1 current that had that funny property once we turned on the background charge. Okay, so you know how current algebra acts on the exponential operators for j-1, you just have a 1 by z on the right-hand side. So if you integrate that formula on a contour surrounding the origin, you get a formula that says that the Q variation of the U1 current is the BRST current. Okay, and that's good because the minimal model does not have a current in its spectrum, so it had better be that it was either not Q closed or Q exact. What this says is that the BRST current is Q exact and the U1 current is not closed. Okay, another important example, which at least for me was useful, involves the reflection of the identity. Okay, so that's the exponential operator. So there's a degeneracy in the spectrum of the linear dilaton. There's always two operators with the same conformal dimension. That's basically a reflection of the p goes to minus p degeneracy in the model without the background charge, but it gets shifted once you turn on Q. Anyway, this thing is like an avatar of the identity operator, and it's sitting in this Fock space on the right. And you can also check that for this complex, you only have a single power of Q going into that Fock space. And the exponential operator to the left is just e to the 2i alpha plus. So if you calculate the Q variation on that exponential operator, you will find that it's the derivative of the reflection of the identity. So that's basically saying that this reflection of the identity is kind of like a topological operator. It's not supposed to introduce position dependence inside of BRST invariant correlation functions. And that's good because it's a dimension 0 operator. It would either be a logarithm or it shouldn't introduce dependence. Okay, so we want to try to start assembling all of these pieces into a quantum field theory as best we can, see if we can make sense of it. All of these holomorphic results are extremely suggestive that there should be some real, physical relationship between something like a time-like linear dilaton and the minimal model. But we'd like to package them all into an explicitly local Lagrangian description and pay attention to global issues. In other words, start with the time-like linear dilaton, do a sequence of well-defined quantum field theory operations that turn it into the minimal model. Okay, so the models that we're going to end up considering, they look like sort of like time-like Louisville. So this background charge Q will be imaginary. We'll have two exponential deformations that we can turn on, which are sort of the generalizations of these Dovzhenko-Fateev screening operators. And we're going to just try to follow our nose, treat them using conformal perturbation theory. And it's important that both of these deformations are charged under and therefore break the U1 symmetry. That makes the reflection identification possible because normally if you have a correlation function and you replaced an operator with its reflection, that has a different U1 charge, so you won't satisfy the selection rule anymore, but now you can just compensate that by adding more orders in perturbation theory, essentially. It's another important point that if we deform by a single marginal operator, then only a single order in perturbation theory will contribute to any physical observable, okay? You put in a string of exponentials that has some total momentum, it has to equal some real number, which is fixed by Q, and each order in perturbation theory adds a particular amount of momentum because the deformation carries a definite U1 charge. So there will only be one solution to that algebraic equation and only one term in perturbation theory will contribute. That seems to be lost if you turn on both perturbations because the charges of these two operators are rationally related. So P prime alpha plus P times alpha minus is equal to 0. So if some order in perturbation theory contributes, then if you bring down P prime more of one deformation and P of the other one, that will still satisfy the selection rule. But that's really actually also already an issue in the holomorphic Coulomb gas formalism. Nobody seems to really care about it. You just pick the representative with the least number of screening operators, but in principle, there's a question of why you don't insert this extra combination to determine whether or not it's 0. Okay, so we're going to start by just carefully considering this free theory, which is the time-like linear dilaton. It has a lot of bad properties. You know, the partition function vanishes on all surfaces except the torus because of the charge asymmetry. Spectrum is continuous. There's states with 0 and negative norm. Nothing that we like. You'd like a model with normalizable SL2C invariant ground state, discrete spectrum. But it seems that the background charge prevents you from making the scalar field compact because this term sitting in the axiom, which is linear in phi, breaks the shift symmetry. But that's going to be the first important difference between space like Louisville and the time-like case that we need, because for us, Q is imaginary, which means that although the action itself is not necessarily invariant under a constant shift, the exponential of the action can be provided that you satisfy a constraint on the radius. Okay, so you do a constant shift, then you're basically just integrating the scalar curvature. That gives you the Euler character. And so what you need is to pick a radius so that you get just a shift by e to the 2 pi I inside of the path interval. So that puts one constraint on the radius. It needs to be some integer multiple of root pp prime over p minus p prime. And then we also would like to request that we keep the Dovzhenko-Fateev marginal operators in the spectrum with integer momenta. And that basically fixes, for generic p and p prime, the radius to be square root of pp prime, okay? So we're going to be working from now on with a compact time-like linear dilaton at this particular radius. So that immediately cuts down the number of momentum states in the model. It makes it a little more natural to pull out these minimal model exponentials since it's a discrete spectrum instead of a continuous one. And more importantly, it also introduces a new set of operators with winding. And they're never really discussed in the Coulomb gas formalism, really because most of the work is done holomorphically, but they'll be important in our construction. And as I said, the compactness of the 0 mode is important because it means that when you sit on resonance correlators, you don't actually get a divergence. Okay, so so general operator with momentum and winding looks like this. You can work out the dimension and spin of these operators. Importantly, if the operator has winding, then generically it will have spin. So now we're going to just consider, again, these set of operators which have conformal dimensions that match the minimal model primaries. So since we are in a diagonal model, they don't have spin, so they also don't have winding in the linear dilaton. You just choose the momenta to again be linear combinations of alpha plus and alpha minus. And we also still have these two marginal operators, which are sort of the right moving completions of the Dotsenko-Fiteyev screening operators. So the other operator that we need to keep track of is the analog of Felder's BRST current. And this is the piece which is, in my opinion, a little bit bizarre. So the current has to have spin, so it needs to carry winding. But actually, if you work it out, this current, if you want to reproduce Felder's construction, actually carries fractional winding. Okay, so I'll say more about that in a moment, but let's just proceed for a second. So the point that I want to make first is that, considering the full model lifts this degeneracy that you had between the two different roles played by these special operators with momentum 2 alpha plus minus. Sort of the screening operators, they pick up right moving pieces and they become marginal operators, while Felder's BRST current, the thing that he was using those operators for, it picks up winding and stays a current, okay? Now, the fact that the BRST charge carries winding means that an insertion of the BRST charge in the correlation function of the minimal model exponentials vanishes because of winding conservation. So we turned on marginal deformations, but they didn't carry winding, so they didn't break the winding symmetry. Okay, so this sort of BRST invariance of the correlators, which is related in some way to singular vector decoupling, is sort of made manifest by this winding symmetry, which looks kind of like a ghost number. Okay, and it also means that the full BRST complex, based on a single minimal model Fock space, will now involve operators with non-trivial winding. Okay, so there's a lot to digest in this screen. I'll just point out a couple of, so this notation, the Fock space, the indices on the right refer to the momenta, and the subindex on the left refers to the winding. Okay, and the operators which are supposed to enter the partition function with a plus sign are the ones in blue. And you can see that there, even though the BRST charges have this weird fractional winding, everything which is contributing with a plus sign to the partition function actually has integer winding. There's nothing weird really about those Fock spaces. And all of the sort of bad, weird ghost Fock spaces, they do have fractional winding, but it turns out that all of their momenta are actually multiples of P. So they still have integer spin, even though they have fractional winding. So,
where is Felder's complex inside this?
Yeah, so one, the original complex that Felder would have done, you just take the horizontal line in the middle. So FRS 0 going to the right and to the left. The point is that, so he didn't label them in this way because he's working holomorphically, and you can't really distinguish between momentum and winding in that case. But he would have had one going directly horizontally, and then the Q bar complex would have been going vertically right in the middle. And then you have to sort of fill it out in the other directions. And it's sort of some non-trivial fact. It's sort of some non-trivial fact that if you take the trace with this particular set of signs with -1 in these ghost Fock spaces, you actually land on the minimal model torus partition function. So all of these different states with momentum and winding, they conspire to cancel, and you really just get the contributions that are sitting there in the minimal model. So, to me, the fractional winding of this BRST current is awkward. It's really a reflection of the fact that Felder's original current was not mutually local with all of the minimal model exponentials. So that's why he needed multiple contours of this current in order to get a well-defined action of Q on the Fock space. So, normally it's a no-no to have fractional winding in a compact boson, because then not all the operators will be mutually local with each other. Here, I don't know that it's a requirement that all of these non-physical operators that are not really supposed to be there in the model have to be mutually local with the physical ones. So all of the actual minimal model exponentials, there's nothing wrong with them. They're all local with each other. They have well-defined correlation functions. The rest of this ghost part of the theory, it looks weird, but maybe that's okay. I don't know. I find it awkward, and it would be nice if there was a better formulation, but this is the best that I was able to find.
But doesn't the BRST current have to be mutually local for contour manipulation?
So the point is that the BRST current, the actual BRST maps in the complex, they don't always involve a single contour integral of that current. So it's multiple nested contour integrals, precisely so that the multiple integral does have a well-defined action, and they do close when they act on an operator in the Fock space. So that's why it's not just a single Q which move you from each Fock space to the next. It's different powers of Q. And
that's very helpful, thank you.
You can read off the power basically by that argument.
And sorry to interrupt, but I think it has been past an hour by now. So even though I know you are just about to get into the interesting stuff, so I wonder, would it be good if you take 5 or 10 minutes to kind of wrap up, and then for those who are interested, we can discuss in more detail afterwards.
Okay. Yeah, so let me skip this point then. The point here is just that there is something which looks a little bit special in this construction about the 2, P models, in the sense that you can set things up with a single BRST charge in the maps between the Fock spaces. Okay, so all right, the last thing that we'll discuss just in 5 minutes is the dynamics, how to reproduce the correlation functions of the minimal models from this BRST quotiented time like Louisville. Okay, so we just kind of want to follow our nose, see if we can treat these exponential interactions using perturbation theory. In space like Louisville, that's not really the right thing to do. You can sort of get the right values for some correlation functions in that way, but then you have to do some clever analytic continuation to get the rest of them. Here, we're actually only interested in the ones which can be screened by integer numbers of exponential interactions. Okay, so the first basic thing to understand is just how is it that 2-dimensional surface integrals can be factorized into these answers that you get with the Coulomb gas formalism, which are products of the Dovzhenko-Fatayev line integrals. The point is just that when you do conformal perturbation theory, you'll end up with integrals of this type, which generically diverge due to short distance singularities in the operator product expansion, which you then integrate over. So you have to figure out how to regulate them in some way. And actually the standard way to treat these integrals just factorizes them into products of the Dovzhenko-Fatayev line integrals, which you then define by analytic continuation from regions of parameter space where the integral is convergent, okay? So that, it may sound a little bit mysterious, but it's actually really just the KLT double copy in a sort of unfamiliar setting. So maybe since we're in a hurry, I won't do this example in detail, but there's a pretty standard recipe that you follow to turn surface integral like this into products of Dovzhenko-Fatayev line integrals. You sort of take this Euclidean coordinate, you Wick rotate to Lorentzian signature, and that puts the integrand in a form that looks like it can be factorized onto light cone coordinates. Okay, and then you need to sort of massage the contours and see which pieces do and don't contribute. And if you do that carefully, you land exactly on Dovzhenko-Fatayev-like expressions. Okay, I was also going to discuss the zero mode quantum mechanics just because it has some interesting differences between space-like and time-like Louisville. So, the exponential for the zero mode in this case is a phase, which is a little bit bizarre. It's obviously not Hermitian. And it's also quite different in the space-like Louisville case because, it's not an unbounded potential, it's complex, does it really make sense as quantum mechanics? But the quantity I times x is actually famously PT symmetric. So although the Hamiltonian is not Hermitian, it is still PT symmetric, so it has a chance of having a real spectrum and real eigenvalues, and you can actually just solve it exactly. You can make a change of variables, which basically turns this into a Bessel function equation. And so, okay, so the eigenvectors are Bessel functions. The Bessel functions have branch cuts generically for generic values of the order. And since the actual argument is complex and sending x to x plus 2 pi r moves you onto the next sheet, you actually need to require that the eigenfunctions don't have branch cuts. And that actually quantizes the spectrum and gives you a nice discrete spectrum. And for those particular values, these Bessel functions, they satisfy what you might call a reflection identification. And they're also entire functions with the Taylor series in W, but since W was basically a plane wave, these eigenfunctions look like they have support on an infinite number of plane waves, which is much different than the case in space like Louisville. Okay, so the last piece, and I'll be brief. We just like to see how to read off truncation rules in this model using basically just kinematics. See if we can get it just from the U1 selection rule. And the easiest way to do it is with an example. So we'll just take the Yang-Lee edge singularity that has a single primary operator along with the identity. It has a very simple fusion rule. And the selection rule on the momenta in this case is just that the sum on n minus 4 times the order and perturbation theory equals 6, okay? So the sort of primary operator that we're interested in is V, which is just e to the 2 over r phi. And we'd like to see truncation of the OPE within this linear dilaton. So the sort of key point, what makes it possible, is that if you consider factorizing a 4-point function onto 3-point functions, because of this funny charge asymmetry in the model, the thing which you're inserting is really O tilde, not O with O. So the OPE coefficients that enter are not OPE coefficients squared, but products of two OPE coefficients, one which involves the operator and the other which involves its reflection. Okay, so the constraints for what can contribute come from being able to screen both the OPE coefficient or the 3-point function on the left, which involves O, and also the one on the right, which involves O tilde. And so you can just read off the algebraic equation for which, which orders in perturbation theory would contribute for a particular operator with momentum n. And the point is that because one of the OPE, one of the 3-point functions involves the reflected operator, the sign of n flips in the second equation, okay? So if that hadn't happened, then there would have been an infinite number of operators which could have potentially been exchanged. But because of the sign flip, there's actually only two shared solutions to these two equations. N is equal to 2 and n is equal to 6. And those are just the two operators which you expected to show up in the Yang-Lee OPE. So the lesson here is that it's okay for one representative of the OPE coefficient to be non-vanishing, provided that the other one vanishes. And we can discuss that a little bit later because there's been some confusion in the literature. And if you follow this basic procedure, you'll actually be able to derive the fusion rules for all of the 2 comma p models, assuming that you only deform by the single marginal operator with momentum alpha minus. That's important that a single order contributes because you can try to play the same game for the more general PP prime models. And there you can see that it's not enough to deform by a single marginal operator. You won't be able to screen all of the correlation functions that you need to be able to compare with the minimal model. So you really have to turn both on. And you can do the same manipulation to determine which operators can contribute through exchange. It basically amounts to finding different ways to split up the total number of screening charges into the 2 3-point functions. And if n plus and n minus in this formula are the minimal value, which is needed to screen the correlation function, you actually find that the only operators that contribute are the ones that are supposed to contribute from the minimal model fusion rules. But if higher orders in perturbation theory were to contribute, so n plus and n minus are larger than their minimal values, then that range increases, and you can't see it just from the kinematics of the selection rule. Okay, so, I don't have a proof that the higher orders in perturbation theory don't contribute, so I really only claim to completely understand the 2, p models where you can deform by a single marginal operator. It seems like there might be an argument that the higher orders don't contribute, essentially because those higher orders, they involve inserting a pth power of this marginal deformation, which once you put it inside the correlation function and factorize it, looks kind of like the Brst charge to the pth power. And in fact, if you were just trying to do this in the holomorphic Coulomb gas formalism and had no ideas which contours you were supposed to use, this is exactly the thing that you would insert. But Q minus, so that operator looks like Q minus to the P, and Q minus was this differential, which essentially satisfied Q minus to the P is equal to 0. So I don't know whether or not this can be formalized into a proof or not, but it looks kind of suggestive. And I think if it is true that in the more general cases, perturbation theory does truncate, my guess is that it has something to do with this slide. Okay, so I apologize for going over. I'll just close with a couple of things which I think are left to understand. So obviously there's this question about the truncation of perturbation theory. If you turn on both deformations, I think that's extremely important if we want to actually make a statement about the general family of minimal models. There's also a confusion that I have regarding the torus partition function, which is that, so, I evaluated it in front of you essentially algebraically using a BRST quotient, just a trace in the Hilbert space, but I think you should be able to reproduce it as well using the functional integral. And there you would need, or seem to need, some discrete term in the action which was capable of producing these minus signs in the sum over instantons. And I don't think there's a term that you can write down with the ingredients that I've included so far. So it might be that there needs to be some discrete gauge field or some other kind of discrete ingredient which is important on higher genus surfaces, but which you sort of are blind to on the sphere. Okay, so I'll end there, and then maybe we can discuss if people have questions.
All right, thank you. Any more questions for Dan?
I just have a naive question. It's just something that I want to understand better. This is related to the, I think you called it Saad Schenker Stanford picture, and I just want to understand. So on one side, you have an integral over the moduli space of curves, and you're saying that you can compute it as a sum over random triangulations on that surface, or?
Yeah, that was the old heuristic for doing gravitational path integrals with matrix models, was that you sort of...
I mean, it's the matrix, it's a Hermitian matrix model in that case. That's an old story. But so in one, what do you exactly mean by random triangulations? So it's summing over all possible triangulations that a genus G surface can have, but then the triangulation must somehow be special, that it's an ideal triangulation or something.
I'm just referring to the old Tuft argument that the combinatorics of a matrix integral basically counts triangulations of fixed genus surfaces. So if you take the matrix and you expand the integrals out.
Agreed, that's true. That's an old known story. I mean, there's no real explanation for it in mathematics, but it's true that the Hermitian matrix model does give this thing. But then what is it computing on the gravity side? So what is the function that you're trying to, I mean, what is it giving an answer to?
Well, it's supposed to be giving an answer to the gravitational path integral, which involves doing a functional integral over metrics and also matter fields, which are coupled to dynamical gravity. So you imagine trying to do the sort of Feynman path integral over all metrics and all matter fields subject to the constraints. And the claim is that that's supposed to be in the same universality class as this.
This is the last statement was the important one. Okay. That this integral should correspond to the thing calculated for, by the Hermitian matrix model. Okay. Thanks.
I also have a question. I think we discussed this before, but I'm curious about your take at this moment. So suppose I don't care about minimal model. Then does the time-like compact Liouville by itself make sense as a 2D CFT?
Well, yeah, I mean, it depends on what your definition of makes sense is, right? Like in order to define quantum field theories that we like, we make some assumptions about their spectrum and their behavior, and it will not satisfy most of those. But I don't think it rules out that it could still describe some, interesting statistical system. I think people use, trying to remember, I think they use kind of an un-BRST quotiented version of this to describe percolation or something, which also kind of has bizarre properties at the conformal fixed point. So yeah, nothing stops you from keeping the negative norm states in BRST quantized gauge theory, but it's not going to have any of the properties that you would like a quantum field theory really to have. So so yeah, I don't know. I mean, I think ultimately the answer is just if it actually describes a physical system, then then you're forced to consider it. But it has a lot of gross properties that usually we would reject.
Hmm. And in the last part that when you rushed through, I kind of missed one of the punchlines. So from your setup, the correlation function in the beginning will have some surface integral.
Yeah.
And then you say there are some tricks to reduce them to contour integrals.
Yeah.
And the contours that this spits out is precisely the correct contour that reproduce the minimal model 4-point function? Or is there still some freedom or some choice that needs to be made?
No, I mean, I think really the surface integrals are kind of like a shortcut to doing the Dotsenko-Fateev holomorphic story more generally, because, I mean, the point is, you work holomorphically, kind of the starting point is very easy because you're just picking out these integrals, which are easy to do, but then you have to work very hard to get a nice local meaningful answer. When you start with these surface integrals, you're basically putting in that you're going to get sensible local answers because you're just, treating a quantum field theory and perturbation theory, but then you kind of have to work a little bit harder to show that it's equivalent to the original Dotsenko-Fateev prescription. But my understanding is that actually they are really just the same. And I think Dotsenko even, was using these surface integrals sometimes as a shortcut to get the correct combinations in the old days.
I see. So you say because here using the surface integral, the starting point is manifestly local.
Yeah.
So we are.
But it's very complicated. These integrals they're tricky.
Can you say what goes wrong for higher genus? You said the holomorphic Coulomb gas formalism doesn't work for higher genus. What's exactly the problem?
It wasn't obvious after the work of Dotsenko and Fateev that it would be applicable to higher genus. Again, because it's not like you're doing local quantum field theory. It's just some prescription that you cooked up to calculate genus 0 observables. And, the vacuum is BRST invariant. So on the sphere, you don't, if you're only calculating these BRST invariant operators, correlation functions, then you sort of never you never see all of the gross stuff, which is also there in the linear dilaton. But if you go to higher genus surfaces, then that stuff can propagate, and you have to make sure that you project it out so that it doesn't actually contribute to the correlation function. So, you know, if you just did the trace in the linear dilaton at genus 1, you will not get the correct characters that would match the minimal models. But if you take the trace in this BRST complex, then you will get minus signs as well. And that's projecting out basically all of the stuff that you don't want in the model. And so what you get actually is the Rocca-Caridi form of the minimal model character instead of this, you know, trace in the linear dilaton, which would have all of the extra states, which you know are not supposed to be there. So, you know, that kind of opens up the way if you want to just say, I'm going to calculate everything on higher genus by cutting and gluing lower genus stuff. You can do that. It's not, you know, it's not particularly easy, but once you've understood the BRST structure and you do the projections correctly, I think that that's one route. You know, it would be nicer if you could just try to also do it with functional integral, which is what I don't completely understand because I don't understand how to put the phases in just within the functional integral.
Thanks.
I have a question about this quantum mechanics calculation. Could you go to the next slide? Maybe the next one.
This one or the next one?
No, the next one where you were talking about the different power series expansion.
Yeah.
Yeah. So here it looks like you have things with only positive momentum, right? And naively, one would have expected both positive and negative momenta so that everything is covered.
Well, yeah, I mean, one of my puzzles about this zero mode quantum mechanics is that, you know, I don't know how much it can actually teach you because, you know, when the model is on a compact scalar, there's also all of these other winding modes that don't necessarily look like plane waves. So, you know, I mean, this is not going to pick up any of the winding states in the BRST complex as far as I can tell. But the reflection, you know, the negative momenta, I think they're supposed to be related to the positive momenta through this reflection identification. So, in other words, you will not get the correct normalization for the partition function if you trace both over the operators and their reflections. You need to put a 1/2 there. So there is a halving of the spectrum just as there is in space-like Louisville theory. You know, I worked for a long time trying to see if there was sort of a more, you know, quantum field theory actual derivation for that fact. But, you know, this was basically as close as I could come.
The quantum mechanics, you had only one exponential?
Yeah, that's right. I mean, I actually just don't know how to solve the quantum mechanics with both exponentials. I tried, but I couldn't get any. Yeah.
And the fact that the coefficients of the exponentials don't matter is related to the fact that only a given order in perturbation theory contributes. And
that's exactly right. So if you work with correctly normalized operators with the canonical 2-point functions, and you either ensure by only deforming by one operator, or you assume that only the first order in perturbation theory is what contributes, then you can show that there's actually no meaningful dependence on the coefficients of those exponential deformations. So it all just cancels out in the end. That wouldn't be the case if higher orders were contributing when you turned on both deformations, which seems to me like evidence that probably there is some truncation in the general case. I just didn't manage to prove it yet.
Is there a conceptual way to explain that rather than doing a computation?
Well, I mean, the closest conceptual explanation I have really is this slide, is just that the higher orders in perturbation theory, they sort of look like Q minus to the P. So maybe you can deform those contours onto other operators and they kill they kill the correlation function. But you have to be really careful there about understanding the actual contours that are being taken, because Felder's construction has specific contours. But you know, I don't know a better explanation than this, and this is really just kind of a cartoon for what might happen. But this would be sort of like to form the contour argument for why it happens.
And can you hear me?
Mm-hmm.
Another funny fact about minimal model partition functions is that they can be written as differences of C=1 free boson partition functions at different radii.
Yeah, that's
or one of them is the radius that's important for you, and another is like that radius over P or something like that.
Yeah, you can see that in this this gross graphic here, actually. So
oh, really?
All of the blue Fock spaces, they have integer winding and integer momenta. So these are basically filling out all of the things.
Oh, I see.
The C=1 partition function at radius P prime, which is in red.
Oh, nice. I see.
Fractional winding, but the momenta is a multiple of P. So it looks like for those guys, the natural radius is actually 1 over P times that radius. So it's sort of like the bad sector just kind of wants to live at a different radius than all of the operators. It seems like that's kind of what Felder's construction puts in. But yeah, I mean, you can check that this is just, it's 1/2 times Z of root P prime minus Z of root P over P prime, or P prime over P.
Cool, thanks.
Would you skip over this red sector and just define an operator, which is the composition of the two? That doesn't make sense. Yeah, sorry, no.
Going on the diagonal?
No, what I said, doesn't make sense. Well, no, maybe it does make sense. So let's see if you, for the red sectors, the image of one is in the kernel of the other, right? So if we were to compose them, I would get 0, right?
Yeah, the image of, well, let's see.
So if I take the arrow that comes from the left and the arrow that goes out from the right, and I just multiply the two operators.
Yeah, that's supposed to be 0 for correctly chosen contours.
Thank you.
Yeah, maybe one other thing, since we're discussing this BRST complex, I'll just say, since I skipped over this. So the 2, P models are a little bit special, well, for several reasons, as we saw. First of all, they only require 1 marginal deformation, but also for those guys, since P prime is equal to 2, the R is always equal to 1. And so I've been using Q minus, which is these integrals of e to the 2i alpha minus to set up the BRST complex. You can also use Q plus, because it's basically the reflection of that operator. And if you look at the way the complex looks for the 2, P models using Q plus, you see actually that only a single integral is needed for each map from Fock space to Fock space. And this is related to the fact that in these models, J plus is actually mutually local with all of the minimal model operators. So it kind of looks like, so even though I'm working at a particular radius, which in this case would be square root of 2 times P, and we find that the current has winding 1/2. In this model, all of the minimal model exponentials have momenta, which is an even number. So it kind of looks like it would rather live at a radius which is 1/2 of what I'm using. And in that case, it would be equivalent to choosing R to just be alpha plus, essentially, okay? would be square root of P over 2. And that would have been sort of a naive guess for how to complete this model, because when they were working holomorphically, they're choosing left moving momenta, which are like some integer times alpha plus some integer times alpha minus. So you could have thought, well, maybe we should interpret that as alpha plus is the radius, s minus 1 is the momentum, since alpha minus is 1 over alpha plus to a sign, and we'll interpret 1 minus r as the winding. But that wouldn't make sense, because then in the full model, if these operators had winding, then they would have spin. But you know that the operators in the diagonal minimal model don't have spin. So generically that would be incorrect, but when p prime is equal to 2, r is equal to 1, and actually this state wouldn't have winding. So it makes me suspect that maybe there is something a little bit special going on for this special class of 2 comma p linear dilettantes. I haven't completely understood that yet.
Yeah. Just one more comment on the 2 comma p case. This is related to Scott's question earlier. So yeah, as Scott was saying, and as also followed from the complex, the minimal model, the 2 comma p minimal model partition function can be written as linear combinations of the c equals to 1 partition function. And that linear combination has a natural physical meaning in addition to the complex that Dan presented. So you can just think about the c equals to 1 theory as a fermionic theory. You can fermionizing, or you can think about it as a Dirac fermion turning on the 4 Fermi interaction. So that's a c equals to 1 fermionic CFT. As a fermionic CFT, you can consider partition functions with different spin structures. And the identity you mentioned, Scott, is just that the 2 comma p bosonic torus partition function happens to be proportional to the Riemann sector partition function of the c equals to 1 fermionic theory at the appropriate radius. So the simplest example is the following. And I emphasize the word proportional because there's a subtle factor of 2 in that relation, as you probably also know. So the simplest example is to take the trivial minimal model, the 2 comma 1. So the partition function of this trivial minimal model is 0. And that corresponds to the c equals to 1 free Dirac fermion without the 4 Fermi interaction. And the Riemann sector partition function of the free Dirac fermion is 0 because of the fermion 0 mode. And that's why 0 equals to 0. And the next simplest case is the 2 comma 3 minimal model, which whose partition function is 1. It's also a trivial partition minimal model. It only has an identity state. And the corresponding c equals to 1 theory is the first n equals to 2 minimal model. In the first n equals to 2 minimal model, you can think about it as a supersymmetric Landau-Ginzburg model. And it famously has 2 vacua. So the Riemann sector partition function of that n equals to 2 minimal model is computing the Witten index of that n equals to 2 minimal model. And the answer is 2. And when you divide 2 by 2, you get 1. And that's the 1 for the 2 comma 3 minimal model. And it goes on.
Yeah, I mean,
nice, thanks. That's very helpful.
I feel that actually, yeah, I think that the BRST, well, my suspicion is that the whole BRST discussion actually would be much more natural in sort of a fermionic version of these models. So you can see this very clearly in the 1 comma 2 case, which, you know, it's not actually a minimal model. It's not supposed to have any local operators. But you know, so sometimes the way that people describe that model is in terms of the eta c system. So it's anti-commuting 1 spin 1 operator and 1 dimension 0 operator.
Yeah, the eta c.
And in that model, really the eta 0 mode really is just the BRST charge. So what you can see is that, so, you know, oftentimes people use the eta c model to bosonize the beta gamma ghost in the superstring. And this question of whether or not you keep the C0 mode or not. And that's like the big Hilbert space versus the small Hilbert space. But if you interpret eta as basically the BRST current, what you have is that the BRST variation of the Xi operator is just the identity, right? Which explains the fact that you don't have any actual operators in the cohomology, because the identity operator is just the Q variation of Xi. And my suspicion is that, so it works really nicely, and I put a couple of pages about that in the paper. Mm-hmm. One question that I have is whether or not you can kind of view the Coulomb gas at these rational values of Q as sort of a bosonization of the BC system, which would be the eta Xi at that particular value of the central charge. Because I feel that this BRST construction is a little bit gross. Nobody really loves it that much, but at least for the 1,2 kind of unphysical minimal model, it looks really natural there. And it would be nice to know if maybe that's kind of a nice explanation for it, but I don't know yet.
But that's but how is this related to the C = 1 model?
That wouldn't be a relation to the C = 1 model. It would be like a bosonization of the BCs. So actually, the first time that Feigen and Fuchs did the analyses of these Fock spaces, they actually didn't use the linear dilaton. They used what they called the space of semi-infinite forms, but that really just means two-dimensional fermions. So, and if you're not being careful and you're just working holomorphically, you don't really make any mistake. And that kind of later got bosonized into the Coulomb gas discussion later on. But I feel that they should be related, and it might be that part of the discussion is more natural in that language. And I mean, this 1,2.
But there's something I don't understand in that proposal. So are you trying to say that for the C = 0 case, okay, on the one hand, we have the trivial minimal model, the trivial minimal model whose partition function is 0. And on the other hand, we have the eta Xi model. And you want to say, you want to interpret their relation in terms of bosonization? Is that the proposal?
I'm not sure, something. So it's C = -2 for the 1,2 minimal.
Oh, sorry, C = -2. My mistake. Yeah.
Gravity is 2,3.
But my complaint is that bosonization is an invertible operation. So when you can bosonize a system to another one, and then you can fermionize back. But in this particular case, if we the model we end up with is the C = -2 trivial minimal model, it doesn't seem to have any content so that we can regain the eta Xi model via some fermionization.
Yeah, I mean, the one thing I would say is, I was looking at that model because basically I wanted to know, what is it that you're supposed to put in the Coulomb gas functional integral to compute 0 in that model, right? Mm-hmm. I don't know the answer to that, but in the eta Xi description, it's pretty obvious that you get 0 from integrating over the 0 mode of Xi. So you're supposed to basically pick the spin structure where Xi has a 0 mode and do that integral, you get 0. That's kind of a natural way to get 0. But I didn't really pursue it.
I don't understand the thrust of your question, Shuheng.
Yeah.
It's often the case when you have the BRST cohomology on one side, and if you know only the cohomology, you might not be able to reconstruct the full theory.
Yeah. So I'm not complaining about the BRST construction, but I thought Dan was trying to interpret BRST as some kind of bosonization or some kind of gauging. I was complaining about that.
Well, as you know very well, many times when you gauge something, there's no, you can try and go back to the original theory, but there's no unique procedure to do that.
Yes, but there is a procedure to go back. Yeah, I have no problem with BRST because I think you are right that when we do BRST, we lose information by going to the cohomology. But I don't think it can be interpreted as gauging or bosonization.
Yeah, no, all that I was saying was that I think that the BRST construction, which honestly still to this day looks pretty unnatural to me in the Coulomb gas language, might have a nicer description in terms of the BC like model, but I don't know what the actual relation between those two is supposed to be. It's just kind of like the very simplest case that you could look at. It does look extremely natural in those variables. But yeah, I don't know. In general, I would still kind of like a way to simplify this
Right.
BRST destruction. It is pretty unwieldy.
Right. All right. If there's no more question, let's thank Dan again.